3, complexity center, right? Go ahead.
Hello. Happy to be here. I think it's a wave scattering audience is not really my usual audience. Let's see. Also, the room. I was thinking we were going to have the session in the next room that has quite an open view of 2-3 floors. So I think it's better here because you have to look at the screen. Anyway, so the title is what you can read there. It has localization, but I'm going to be looking at it from a nonlinear dynamical point of view through an analogy. And I'm going to be referring to possible connections, possible presence of localization in other types of systems. This is the outline. So I will have a preamble. The tangent bifurcation, it's the section that actually deals with nonlinear dynamics. And then we'll see an analogy, and then we'll end up, let's see. I want to mention 3 things. First, synchronization, then the phenomenon of localization, and then nonlinear dynamical phenomena. And putting them together, what is mentioned there, it's a cross-fertilization, whether the 3 topics make sense in a single talk. Here we have something to attract your attention. It's a very nice photograph. It's a collection of half a dozen photographs of murmuration of birds, starlings, for example. And these photographs are actually, you can follow the single bird a long time. So you see this phenomenon that of collective motion, that some well-known examples. For example, you have schools of fish, sardines, you have fireflies, you have, in many cases, you also have this, for example. You have this collective behavior. So these are the visual first 2 slides, and then we go into, okay, so we're talking about synchronization. Maybe the few lines were taken from Wikipedia or something like this. So there is a broad range of, say, dynamical systems, including neural signaling, beating of the heart, synchronization of far flight, and so on. And we have a typical model system that is studied. It's the arrays of oscillators, coupled oscillators, globally coupled. That's the Kuramoto model. And here you have is a set of first-order differential equations, all coupled. This would be the Kuramoto model. Here you have the phase of the oscillators according to coupling strength. And here you have the yellow circle, perhaps that points out something like center of mass. So as you increase the coupling, you don't observe phase locking, and then it appears, and finally you have phase locking. In the sense the oscillators become synchronized. And I'm going to point out these 3 statements. First, that in the infinite size limit of these coupled oscillators, they display low dimensional dynamics. So it is a collapse, a drastic collapse in the dimensionality of the system, from basically infinite to low dimensional dynamics. And here would be, for example, a typical reference. It's already 10 years or more about that. Then this is relevant because of the previous talk, for example, it was mentioned that the intriguing fact is the invariance of the Poisson submanifold. What it means is that if for example, if the initial phase density is a Poisson kernel, it remains a Poisson kernel all the time for these coupled oscillators. And a third statement. The original microscopic dynamical state of a large number of phase oscillators can be reduced to a macroscopic collective state where the governing equations of the system are generated by a Mobius group transformation. All this happens to the Kuramoto model or to arrays of oscillators. Then these two slides are coming up are not for a scattering wave audience, for a wider audience. So I'm just not saying only general things. For example, that's the topic of wave propagation through scattering media, the phenomenon of localized states in terms of the probability to find an extended state, just to mention the size of the system and the localization length, and the fact that the phenomenon can be observed for other wave propagations in other media, and so on. So that's the reason for that. And also this slide in which the Anderson localization is a general wave phenomenon. It's a repetition of the previous thing, but it's just in order to present the matrix procedures, the transfer matrix and the scattering matrix, and the notation perhaps we're going to use for reflection and transmission coefficients. So this is a question for this talk, whether there are similarities or there are connections between synchronization and localization. So we have here just arrays of oscillators that are coupled to each other. I mentioned already the Kuramoto model. And here we have the propagation of waves through different media. And the media is composed of scatterers. And we're just saying whether there are similarities or connections. And to proceed, I will be talking about some very basic facts or properties of simple, low-dimensional, nonlinear dynamical systems. That means iterated maps, for example. And so we have this picture, which I think is very familiar. It's just a bifurcation diagram of a very well-known simple iterated map. I think perhaps that this picture is the picture from nonlinear dynamics that it's better known by everybody, not academics, academicians or scientists or so on. And we're looking at, so we have in this bifurcation diagram, we just have a control parameter, a single parameter that is run from small to large. And we have a phase space or that defines the interval in which the mapping is defined. We have, for example, we're just focusing on certain features that interrupt the chaotic attractors in these quadratic maps. And these are these windows of periodicity of different widths. Here is the largest one. that corresponds to period 3. That means as we move the control parameter of the map, we reach a limit. We have a chaotic attractor that suddenly, sharply transforms into periodic 1 and period 3. And then we have this window periodicity. We have basically the same cascades of duplication of periods and periodic band attractors and so on, and we can entertain ourselves with these very well-known families of attractors. So I want just to pay attention to the edge, to the left-hand side edge of this window periodicity. And locally, if that map, the mapping that describes that situation, is just locally seen in blue. It's a map that is close to tangency to the identity line in green. And it's actually not quite yet tangent. So we have a trajectory in red. And that trajectory goes through a bottleneck and passes through and perhaps is reinjected. And then we have the phenomenon of intermittency. Of course, if the map is brought to tangency, well, the trajectory gets trapped eventually by a single point attractor. And this situation can be studied in detail. It had been studied in detail some time ago. It's amenable to the renormalization group technique. And we're going to be referring to what is the renormalization group fixed point map for that situation in the nonlinear dynamics. So we have the same situation, a local map at tangency. We're writing an expansion around the point of tangency. In the case of the window 3 periodic window that I was pointing out, this little n would be 3. And we're looking for a map that satisfies this equation. The transformation is just functional composition. It's iteration of the variable. So we want to find if there is a solution to this equation, whether there is a map such that functional composition is exactly the same as rescaling. And this problem was looked about by Bambi Hu long ago, and the solution is written down here, for example. Here is this map, and here is the result. Z is the nonlinearity, and there is a notation to write down this closed form analytical expression, and here are the definitions. It's what's called a deformed exponential. It's just what we're showing here, and if the deformation exponent q is taken to 1, one recovers the ordinary exponential. And the inverse function is shown here, is the deformed logarithm. They are inverse functions, and it becomes the ordinary logarithm. In the case, the deformation parameter q becomes 1. So it is a clear-cut example of renormalization group fixed point map that captures the soul of that nonlinear dynamical phenomena. And one can go slightly further, and then look at the trajectories, actually the trajectories that take place for that map. And here is an expression for, implicit expression for all the trajectories. Again, I should go further. One can write the trajectories for the fixed point map. X naught is just the initial condition. U is the curvature of the map. T is the iteration map. So all trajectories for this mapping obey the same expression. You can rescale them just by changing the initial condition, just by changing the curvature of the map. You can, that's the present that randomization group technique gives to us when there is a scaling. We can write down an infinite family of trajectories with a single expression. And one can also find out a central quantity in nonlinear dynamics for these simple nonlinear systems, which is the sensitivity to initial conditions, to see how trajectories converge or separate from each other, and the Lyapunov exponent. Well, at tangents, this can be done analytically, and here it's in yellow the result for the sensitivity to initial conditions. And let me say that at tangency, which is transition to chaos or transition out of chaos, as we saw, we were in a chaotic situation, and by moving the control parameter, we abandoned chaos and landed in periodic motion. It's a route out of chaos. And at these transitions, the Lyapunov exponent vanishes. Now, since we're going to be talking at least about localization, let me say that what we're going to find is that there is a connection between localization and a transition into or out of chaos. And that the Lyapunov exponent in the nonlinear dynamical system is going to be the inverse of the localization length. So that's why I'm showing you this and numerical corroboration and no more. I think we're ready to abandon nonlinear dynamics and move into localization. So what do we have? We have a specific model system that was worked out by colleagues here in Mexico, or the organizers, in fact. Here we have the name of Moises Martinez. And this is a lattice. It's called a double Cayley tree. It's just made up of the beta lattice, one branch, another branch, and sewn together. And so we have this double Cayley tree. And in order to look at the problem of localization, for example, we place scatterers at the nodes, identical scatterers. And then we pass through a wave, say charges, and so we have a problem for localization without disorder, if you want, and for a very simple lattice arrangement. And what we had, it was an analogy. Here is the reference, but it's an analogy between this problem of electronic transport across this network of scatterers and the onset of chaos or transition to chaos I was just talking about before. And so it goes by something that would be familiar for all of you. It's chosen to be the scattering matrix. That would be the scattering matrix for the scatterers, single scatterers. Here you have this parameter epsilon, which would be just a transmission probability. And you have these coefficients that made up it's taken to be of coordination 3, this double Cayley tree. It could have been a simple chain. It could have been just what you saw in the picture with coordination number 3. It could be 4, 5, whatever you want. And that's why it is a 3x3 matrix. And what it's also the scattering matrix for the entire lattice can be worked out. It has this simple form, and these are also familiar conditions that you see in your applications, like unitary because of flux conservation, and time reversal symmetry makes it symmetric, but the double Cayley tree helps. It's symmetric for reflection, and so you have this form for the transmission and reflection coefficients. It can be diagonalized by 45-degree rotations, and you have these eigenphases. And what is this, what we have here? We have a recursion relation between two scattering matrices for lattices that are of different sizes. This little parameter n is the number of generations, the number of branches. It's branching out. And then it's branching down back. So it branches n stages and then retracts again n stages. And we my colleagues, my colleague at the time, Moises Martinez, obtained this recursion relation. It's a recursion relation between two scattering matrices of two double Cayley trees of different sizes, just different in one generation. Maybe you can see here's little n minus 1 and little n. And this gives us an expression for the phase, how the phase theta sub n changes according to this recursion relation. And with that, one can obtain the transmission coefficient, and one can obtain the conductance, Landauer's formula. And so we were done. But yes, just look that for other people, I mean, other than Moises, meaning myself at the time, this is just a map. It's a nonlinear map, low dimensional. So let's look at that map. And here we have the map for fixed transmission probability epsilon, and moving the parameter that would be related to the energy of the beam, which has to do with the lattice spacing so the map has two branches. Look at the solid line here. It has this branch and it has this other branch. And if I move the parameter, the control parameter, it has two. In terms of nonlinear dynamics, this mapping has two control parameters. One is epsilon, and the other one is k multiplied by a. And as we have seen, it has to do with just the lattice spacing. And we keep one fixed, and we move the other, and then you go from the solid line to this dashed line. So it has these two branches, or to these shorter dashes. So you see you're bringing down one branch to tangency, while the other one is being taken out of tangency by varying this control parameter. Here is a similar situation in which one looks at the map of tangency, one branch of tangency, at tangency, and beyond tangency. And here, small, but we see it larger, have the bifurcation diagram. This is the bifurcation diagram. And what does that tell us? Well, here it is, the bifurcation diagram. It tells you that there are two types of regimes. You have one regime in which the attractor is a single value of the phase. That means all the phases are the same. You have this attractor. In nonlinear dynamical terms, it's just a period one attractor. And then you have a tangency, a tangent bifurcation. You enter a chaotic regime. Here is the chaotic attractor. And then you enjoy it, and then finally leave it again for a period one attractor. So I'm also writing down here that in the chaotic regime, already going to mention, look, there is an invariant measure, an invariant distribution. That means the positions are dancing around because a chaotic attractor, but there is a density, a measure, which becomes invariant for very large iteration times. It's the invariant density of the chaotic attractor. And that happens to be a Poisson kernel, which again is being mentioned a number of times today. Here is a little bit more detail. It says, okay, we can calculate the sensitivity to initial conditions. Here it is. For large iteration time. If the iteration time grows and grows and grows and approaches infinity, this will become the Lyapunov exponent. We also have the conductance. The conductance obeys, let me say, because I'm not being clear, in these simple non-linear dynamical discrete problems, one has a variable that we call time, which is not time, which is just the iteration, successive iterations. But here, there is an analogy. We're looking at an array of scatterers, and we are looking at different sizes, different generations n. So iteration time actually means the size of the system. And to make the system macroscopic will take us to very large iteration times. Okay. You're after the conductance. Here it is, the conductance. And then you see that in the insulating regime, it will decrease to 0 exponentially, and it will have a localization length, which is this number z, and turns out to be exactly the reciprocal of the Lyapunov exponent. And at the Lyapunov, at the tangent bifurcation, when the system is not going to be any longer insulating and is going to have non-zero conductance, it's in our mapping just a transition to chaos. And then the localization length will diverge because the Lyapunov exponent vanishes. And then we have the results at that condition. We make contact with what we've been talking about earlier, about the tangent bifurcation. One can obtain everything analytically all the way to the localization length. What we're saying is that the system is so trivially simple that it's paying off. For example, we can actually look at the localization transition, sit on top of it, be at the mobility edge, because it's so simple. That means we're not trying to imagine what happens with the quantities, the scattering quantities, but we're actually able to sit analytically at the mobility edge. And what we have is that actually, this is just numerical corroboration, we have a power law behavior of the conductors. Fine. Now, a little bit more. Time passed, but not much. This is already a good number of years ago. The same group. And what was found out it's in the title of this publication, is that the problem was revisited, and it was found, of course, that the scattering matrix moves around a unit circle in the complex plane, and the way it does it as a Mobius transformation. I'm not going to go through the details because they're the same as before. I'm just going to show the mapping. The author of these plots, I suspect who is the, I think it's Victor. I borrowed them, I placed them here. So you have the mapping, you have the two branches, you have different values of control parameter again, and what we're looking about is these webs, they call these trajectories. For example, you have an initial condition. It's a visual way of saying it passes through the bottleneck, goes out, goes into the other branch, rejects it, and then you have the nonlinear dynamical evolution of trajectories for the map. And this is just to show. And to go back to you, here you have Landauer's formula and so on. What I want to say is that the scattering matrix, here it's written just as a complex number, is in the unit disk. It obeys Mobius transformation. The coefficients for the Mobius transformation are written here for the double Cayley tree with the same parameters. Here is for a chain network. And this brilliant green is the Lyapunov exponent. So the Lyapunov exponent is negative for the localized regime, is negative, meaning trajectories just converge into each other exponentially. Period one, if you want, very simple. But in the conducting regime, in red is the phase, the chaotic dynamics. The Lyapunov exponent remains flat, 0. That means it's a special type of chaotic attractor. Chaotic attractors in general have positive Lyapunov exponent. But there are chaotic attractors that cannot raise the value above 0, and we are talking about weak chaos. And when you have weak chaos, how do we explain this? Well, it's not difficult to see it qualitatively. It's vanishing Lyapunov exponent, because once the trajectories are moving away from one of the branches and are expanding out and building up a positive Lyapunov exponent, they are captured by the other branch and sent back to converge. So they are expanding, converging, expanding, converging, and the net result is that Lyapunov exponent remains 0. And this is associated with the mathematics, or if you want, with the hyperbolic geometry of the Mobius transformation. And that's what we're talking about here.
So, sorry, the red dots, what are they?
It is the conductance. It is the conductance. It is very small. Apologize. Here it says G, and G is the conductance for the red, and it says lambda, and lambda is the Lyapunov exponent. The conductance scatters. But take into account that we are looking at the conductance as we move one of the control parameters, which is related to the energy of the incoming beam. So when it's moving about, if you want to to see a specific nature of the system, then you had to draw just a vertical line. And here in this, I could not answer. I don't know whether you fix the energy and you only have one value. But it's intermittent in the sense of nonlinear dynamical behavior close to the tangent bifurcation, meaning the intermittency is that you go through a bottleneck. That means you, as you go through the bottleneck, it's well behaved, it's a laminar episode, but once it goes through the bottleneck and is liberated, it bounces back. So intermittency is laminar episodes interrupted by chaotic bursts, and that is the phenomenon that is accompanies this route out of chaos. Maybe I should, no, I have time. I have time because I don't have many slides. So, why am I showing this? Well, on purpose, because I started with synchronization. I started with some famous or visible work in which some authors say, look, this simplification that's not supposed to take place. You have problems of high dimensional complexity. You have arrays of oscillators, and it happens that these high dimensional problems can be described by low dimensions. And we talk about a Kuramoto model, and then we are mentioning that there are two technical features to remember: Poisson kernel and Mobius transformation. And then we went into this scattering array of scatterers. We look at the details. We found out that it can be actually be neatly described in the language of nonlinear dynamics, and we find the two ingredients: Poisson kernel for the invariant distribution, and Mobius transformation for the dynamics of the phase. So here it is. So one could move actually into the intricacies of hyperbolic geometry, and that would be very interesting. It is interesting, but no more right now. And then I'm going to be mentioning also this. This is a feature, curiosity of, again, of nonlinear dynamics. For example, here showing you, that's what I captured from the web producing this, so it had to be a simple example. It's just Newton's method to find roots of algebraic equations. And it's taken from Newton's mode. But what he's saying is that if one goes into a nonlinear dynamical problem of dimension larger than 1, here's an example of dimension 2, one can have, for single fixed values of the control parameters, more than one attractor. And here you can see there is one attractor green, one in blue, and one in red. That means the long time iteration stages of trajectories. So one asks oneself, given an initial condition, to which of the three attractors will it go? If the situation is simple, then you will have two attractors, A and B, and you can have the border, the frontier between the two basins of attraction, and say, well, I want to know to which attractor it goes. I have some imprecision in my calculations, so it could be that I cannot decide clearly to which one of the attractors will it go. But all I have to do is reduce I mean, increase my precision, and then I will know. But there is something. If the border between the boundaries between the basins, it's a fractal, like here, you will never know. You cannot decide. And then instead of having sensitivity to initial conditions, you have sensitivity to the final condition. And so, in that case, positions of the boundary, if they are placed there mathematically, fully mathematically, it will remain there. It will remain there forever. And also, in a complicated way, these fractal boundaries, it will remain forever. And when you reduce the nonlinear dynamical problem back down to only one dimension, that's called a repeller. It's an unstable solution. If you place it there, it stays there. But you're never really quite able to place there. So it will be well-behaved, it will be obeying, inside, trying to stay there, trying to stay there. It's not moving away, but eventually it has to give up and move towards the attractor. So this is just to say, here's a picture I tried to put down of the mapping that we've been talking about. It has two branches, the map that gave us the localization and the funny conductance and so on. And what we have is that this weakly chaotic attractor with vanishing Lyapunov exponent has even more within it. There should be positions, initial positions, that give a periodic motion. They can be observed. They can be observed in the same mapping. They try to be, they will be of different periods, all possible periods. Not irregular, period infinity, which is the main attractor, which is chaotic. And if you place it, this is now an elaboration of something that, why am I saying it? I'm just saying that you could have periodic motion in that chaotic region, which meant it was a conducting medium, a conducting set of scatterers. And it can be periodic, but it can also be close to periodic and not remain there forever. This, which has no use at the moment, I use it for the last, well, this is one slide, which is, why not? Why not? We can take the double Cayley tree and place this kind of scatterers. So they're not moving like the birds, but you can hear them sometimes. And let's just read this, which is not fully serious. Well, not fully serious because it's been working out, but just by getting entertained by the problems of localization that we've been looking, or getting entertained by the nonlinear dynamical mapping equivalent to it. And then let's just go quickly. So why not? One can look at these active particles or collective behavior in other systems. Why not with the transfer matrix? Why not arrange them as a double Cayley tree? Why not take again the recursive relation as sizes of the communities? Why not, we already know, I mean, immediately because of what we've been showing, we will have this nonlinear dynamical problem. We will have the families of attractors. We know that we have weakly chaotic or critical attractors because it has been measured. It has been measured, for example, murmurations of starlings in the afternoons in Rome. That's what physicists do in La Sapienza in Rome. They get on top of the churches and they measure the correlations of startling murmurations, and then they find that they don't decay exponentially, they decay more slowly, and so they talk about the correlation length and the power law and so on. So that's why we have this here. So we have, there's no point really in describing them. I ended up in the 9th one with these periodic unstable orbits embedded in the. Anyway, I'm closing down because it's necessary because what I did was to talk lightly about synchronization with certain facts, talked in detail about a simple model of scatterers that can be solved in all detail, and then perhaps you can eliminate the last portion about collective animal behavior. Thank you.
Questions? So in your Kelly tree, finally, the scatterers are all equal. So in a way, it's a crystal.
Yes.
Crystal kind. So essentially, the localized states are the band gaps, and the chaotic corresponds to the bands of that crystal.
Let me.
It's in a way that the wave vector that you are trying to transmit is having different phases along this. It's not commensurate with the period. That's chaos. My way to see that.
Yes.
Not any objection.
No. It is a good point, precisely, because that's what it says here. Disorderless. But for the sake of answering, you have mobility edges for these situations, even if it's just a chain.
Well, that's mobility edge from the gap to the extended band. That's
okay. I'm not going to.
You do not object to calling them mobility edges.
Okay.
It's not
Let's you know what we do in nonlinear dynamics? In nonlinear dynamics, sometimes we put, these are deterministic problems. Mm-hmm. We put by hand noise. And that way, I mean, it is the next thing after solving these bifurcation diagrams, a natural step is to take the same mapping and add noise, whether additive or inside the control parameters. And that's our way of introducing disorder in a system. So again, it would be ready for discussion whether the lack of disorder in the model because the scatterers are identical, how do we expand that situation? How would we move away from them? The one I would use would be to add noise to the map. And then I'm departing from the situation in which you're talking about. In an easy way. There is a more difficult one.
Just a comment, but the result is the same because in this, year we have simulations with disorder. I forgot to say, but again the Poisson's kernel appears. Doesn't matter the disorder.
Let me then add, because it was also no point, it was not crossing my mind. These lines of research that have continued along with the Kuramoto model which are arrays of oscillators. They have moved into heterogeneous coupling. I mean, they have moved from identical oscillators into non-identical. And I have not really followed all the details of the more recent publications, but they seem to be obtaining again this Poisson kernel and features like that. I'm not sure about the, but it's a good point. These in fact are simple problems, and then we should enjoy them because they allow us to obtain everything. And then we're conscious that we're obtaining everything because they've been simplified, and then move away from them.
In these models, there are like some stability of the network. I mean, in the sense that when you have animals, if one animal loses its energy, let's say, then the whole network loses the phase blocking, or there is some parameter to measure the strength of one animal in that position, another animal in that position, even they
well, when I don't know whether it's worth elaborating now or even later about this situation. For example, let me say in a very naive, candid way. When I saw or was aware of my colleagues in complex systems getting very interested in these collective motions, these active particles, I actually said to myself, I'm not going to drink from that water, because it had become fashionable. And again, there were the models themselves, you do statistical mechanics, but they don't have a Hamiltonian. So you put by hand something that is mimicking the directions or things like that. And so that's my attitude. But at one point, I gave up. And I gave up, or I'm giving up, because of the experience with my colleagues from scattering problems, in which it was like when you work out the problem from the end to the beginning. I said, what you have there, the conducting regime, is special. It has vanishing Lyapunov exponent. It's weakly chaotic. It's correlated. And I said it would be a waste not to use it as a different approach to these problems in complex systems. And before looking at murmurations and looking at velocities, well, say, why not? I mean, fix them as scatterers. That's where they were cicada. But let me say, there should be, perhaps is this physical phenomena that can be at least described superficially without any detail of what obviously is happening. I mean, with this, even if they are bacteria. I mean, it's, in fact, is irresponsible for the physicist to construct these models.
More questions? In another case,
Well, thank you for your attention.